Hello everyone, my name is Kavita. As introduced before, I'm a postdoctoral researcher at the Technical University of Darmstadt. And today I'm going to present our work in which we have proposed an approach called Xplain, which is an upgrade on the existing path gradient methods, basically explanation methods, which are used to find out or determine the subtle and the complex relations between the trigger features and the other object and the features of the other object in the input sample, which is the main cause of the backdoor classification. So I'm not going to go into too deep because before me the backdoor attacks has already been explained in detail. But given an access of the training data set to an adversary can integrate triggers into the input sample. And when these input samples are given to the model, so the model misclassifies into an adversary chosen label. So in order to, so the goal here is that in order to design an effective defense system, it is very important to analyze which backdoor features or which input features actually contribute to the backdoor or you can say to the model misclassification. So there is a field of study which is the explainable AI, in which the explanation methods are used to determine which model, which input features are the root or are the most important for the model classification. So if we have this knowledge, like if an explanation method is used like that, so it helps us to identify which specific input features or the patterns actually indicates the presence of the backdoor. Thus, it helps in understanding the backdoor triggered misclassification. However, the existing explanation methods are not that robust enough or are not that efficient to discern these relationship links between the trigger features and between the trigger features and the features of the other objects in the input sample. For example, in the input sample, which is on the left side, the trigger which is a cross has a relationship between with the tree of the input sample. So as a result of this, it is misclassified into to a plain label. But when this particular trigger is moved to the bottom right corner, so this relationship between the trigger features and the tree features is broken. So that's why the model, so that's why the misclassification doesn't happen. So this is our actually motivation in this work, is that to propose an efficient approach or to propose an efficient explanation approach that is first able to discern the features of the backdoor as well as its relationship with the features of the other objects in the input sample. Specifically in this work, we have focused on the path gradient methods, and which are mathematically sound and are known for their axiomatic foundations. So as you can see, there are two keywords. One is the path and other is the gradient. So what it means to be a path, or what is the definition of path in the path gradient method. So there are two variables here which are most crucial to determine the attribution of features in the attribution or the explanation of the features. So there is a baseline, which is the initial feature values, and there is and there is the output image, which is actually also the input sample and which contains the final feature values. So the path here means it means that how the interpolation samples are computed between the baseline, which is the x prime, and the x. So based on the design of the algorithm, how the structure of the interpolation sample is computed, it can take any path. It can take the shortest distance between the baseline and the input, or it can take the path 2, or it can take the path 3. The gradient here, it means that we actually compute the gradient of the model function with input as a interpolated sample with respect to the feature value for which we want to compute the attribution. So this is actually the definition of the path gradient methods. So among these path gradient methods, our focus in this paper is actually on one of the path integrated gradients or path gradient method, which is the integrated gradient, or the IG method, which is one of the most prevalent path gradient methods in the literature, and on which the people have actually developed refinements on this particular IG method. So in the IG method, so as I said, the path actually determines the interpolation samples. So in IG, the shortest distance between the baseline, which is the x prime, and the input sample is computed. And as you can see, the interpolation is the value which is like how much it is increased from the baseline. So these are the interpolation samples, and alpha actually, so the value of alpha actually determines how precise these interpolation samples are computed. So the output of the IG is an attribution vector in which each value in this particular vector determines the contribution of the ith feature to the model prediction. But still, there are certain limitations of the existing path gradient methods, which is the introduction of the noise from irrelevant features to the model prediction. And this particular issue raises from the three causes. So the first one is the highly correlated features in the input samples. So what it means that till now in the path gradient method, it has been assumed that all the features are independent. So if there is a link between two features, so the path gradient methods are not able to compute an efficient attribution vector or the explanation vectors. The second one is the baseline selection. So what it means is that whatever the pixel values are chosen in the baseline according to the explanation method, so they won't contribute to the model prediction. But in reality, those might be the most important features that contribute to the model prediction. So the path gradient methods are actually baseline dependent. So for example, in this particular image, the blue color is chosen as the baseline. So it means that the pixel values in this blue color, according to the explanation method, don't contribute to the model prediction. However, they might be the most important features that contribute to the model prediction. And the third problem is the saturation problem. So what it means that along the gradient path, so the gradient of the interpolation samples actually saturates as the alpha increases. So because of this, after a certain threshold, the gradients, because it saturates, they don't contribute to the model prediction or the attribution map or the explanation vector. So because of all these limitations, the existing path gradient method, they don't perform really well. So our goal in this paper is to remove these limitations and propose an approach that works better first, that is able to in order to remove this limitation, our first contribution is to incorporate a quantitative noise. So the intuition behind adding a quantitative noise is to integrate rapid small alterations in the model predictions or on the path of the interpolated samples. So what it means is that since it's not a straight line, it keeps on changing. So that's why it is able to capture the relevant links between the trigger and the surrounding features. And since because of the noise, it doesn't saturate, it keeps on changing. So it also solves the saturation problem. The second one is to remove the baseline dependency. For that, we just integrate an additional baseline to the formulation of the IG method. So what it does is that it ensures the effect of the baseline features which they persist along the integration path, that is from the baseline to the original input sample. And then lastly, our contribution in this work is the sensitivity analysis. So in this particular, we try to analyze if there are links between two features, then how much this feature actually contributes to, like how much this particular feature actually impacts the first feature. So we create or analyze a distribution map of the most important feature and how the other feature actually impacts the most important feature according to the explanation map that is generated using our approach. So, like I said, first step in our approach is the noise integration. So given the input sample and the baseline, we first add a speckle noise. So the reason we opt for the speckle noise was because it's more distributed across the whole input sample, and that's why we also didn't opted for the Gaussian noise, which is more centered. So now the interpolated samples are the new ones, which is given by IS. Next, we give the input these interpolated samples into the next module, which is the baseline integration. So as I mentioned, we just append an additional baseline to the interpolated samples. So P is the new interpolated sample, and then we input this P into the formulation of the IG, and then we compute the gradient of the model function with input as these new interpolated samples with respect to the feature value for which we want to compute the attribution. So this is a very simple yet novel technique, and which was able to remove the limitations of the existing path gradient methods. So to demonstrate the efficacy of our approach in different domains and to compare our approach against the existing path gradient methods, we considered the application domain like the computer vision, NLP, and the multi-model domain. For these particular domains, we considered the corresponding model architectures as well as the different data sets. And to compare our approach, we considered these 4 path gradient methods. The first one is obviously the integrated gradients, and the last 3 are just the derivation on top of the integrated gradients. And for the trigger analysis, we did the 1 backdoor analysis, the 2 backdoor analysis, and the decoy triggers, which was meant to fool our Xplain. So in the evaluation section, the other explanation method got fooled, but our explanation was perfectly able to determine what were the decoy triggers and what was the true trigger. So this is just a simple evaluation of our approach against the other path gradient methods, and as one can see, our approach is better able to point out the most important features that contribute to the model prediction. In this analysis, we performed, this is basically the trigger analysis. So we compared again our approach against the path gradient methods for no trigger, 1 trigger, and the two triggers. And also we also computed the sensitivity score of the most important features against the remaining features. So as one can see that in the 1 trigger, our approach was perfectly able to discern the trigger features as well as its relationship with the other objects, that is the watch in the input sample, but other objects were not able to do that. In the 2 triggers also, our approach, first it identified the pixels which contributed to the trigger as well as its relationship with the pixels of the other object, that is the watch in the input sample. So this is how we can see that our approach worked, or the improvements that we made on the IG was much better than the previous path gradients method. So in conclusion, like I said, the existing path methods suffer from the noise, and this happened because of the 3 reasons. So the first one was the correlation between the input features. The second one was the baseline dependency, and the third one was the saturation effect. Thus, because of these limitations, it was not able to accurately discern the association rules of the input pixels, or if the backdoors are present, they were not able to perfectly determine the causes for the model misclassification. Then, as a result of this, we proposed Xplain to effectively address the issue of noisy relevance score. And because of this update, the people in the security field can help better design an effective defense mechanism which will be robust against the backdoor attacks. And then we also extensively evaluated our approach against the other paths gradient methods, and it showed that our approach, Xplain, was much better than the existing path gradient methods. Thank you.